Hello everybody and welcome to the module on hyperparameter optimization. I'm Lars Korthoff, and in this video we will talk about local search, a more intelligent hyperparameter optimization method, and related to that, ablation analysis, which allows us to get an idea of how important individual hyperparameter changes are with respect to performance. So the idea behind local search is very simple. We take a random point in our configuration space, and then we look for improvements in the local neighborhood, and we move to where the highest improvement is found. And this is very similar to how you might do this manually. You start at a particular point, and then you look around that point to see whether you can improve by moving in a particular direction. Then you simply iterate this. We have started at a particular point, we have found a way to improve on that, and then we try to improve on that new best point that we have found so far. We can run this multiple times, as in we can restart in multiple different places. We can take multiple random samples to avoid getting stuck in local optima. And this is what's known as an adaptive search, because we take what we have learned about the search space and the configuration space into account when deciding where to evaluate next. Contrast this with the two other approaches that we have talked about previously, grid search and random search, which are non-adaptive in that the result of a particular evaluation does not affect where we're going to evaluate afterwards. We can take all our random samples, for example, before we have done a single evaluation, and then we can plan everything ahead, and that's why we can run everything independently as well. Whereas here, we do an evaluation, and based on that, we decide where to go next. In practice, this might look something like the picture on the right-hand side here. So again, I have taken XGBoost and I have tuned the two hyperparameters alpha and lambda on a particular data set. And you can see that I have done a number of different optimization runs with local search here and there and down here and here. I start in a particular point on the direction of the arrow, essentially shows you where it's moving. And for example, here we can see that we start at a point that is okay, not great performance, but certainly better than what we have observed over here. And we start moving in this direction here, then we move up there until we eventually end up here, where we do observe substantially better performance than what we have started from. So this is an example of how this is adaptive. We move in that particular direction. We don't look in the other directions because we know that we can't find anything better there. The advantages of local search include that it is conceptually quite simple. It makes sense, right? This is what you would do as a human, and as I have mentioned, it is adaptive. The later configurations depend on the performance of the earlier ones, and we're not as likely to search irrelevant areas as we are for random search and grid search, for example. It is also relatively easily parallelizable, not quite as easily as for random search and for grid search, because we do have the adaptive bit, and we do need to know what happened in the previous evaluation before we can move on to the next one. But we can start in many different locations, and as you have seen on the previous slide, this is quite beneficial, and we can run all of those local searches independently. So we can parallelize over the restarts here. Disadvantages include that I have to define what a local neighborhood is. So essentially, what is a small change to a hyperparameter that makes sense here? This often requires discretization with all the disadvantages that we've talked about before for grid search. And this can be not entirely obvious in practice, in particular because it also might depend on the data set that we're working with. So we do have a little bit more of a setup cost in that we need to define what the method does and how it does it than for grid search and random search. We might also need a large number of evaluations if the starting point is very far away from an optimum. We can get around this by doing the restarts that we have seen on the previous slide in the graph here, because there, even, for example, if we start here or over here or even there where we really observe very bad performance, it doesn't matter so much because one of our random points will hopefully fall into an area where we have better starting performance, and that means that we can more easily find something that is good and find something that is a global optimum. So Based on the idea of local search, we can also do ablation analysis, which essentially allows us to quantify how important hyperparameters are with respect to performance improvements that we have observed. So the idea here is that we take an optimized hyperparameter configuration, so something that was found by a local search, for example, and we take something to compare it to. And that could be, for example, the default hyperparameter configuration for the particular learner, which is usually what we would start from. And then we change the configuration greedily, one hyperparameter at a time, until we have reached the target configuration. So say that there are 3 hyperparameters that are different between the initial and the target configuration. We flip one of them at a time, see which one has the largest impact, then we lock that in and we iterate that process until we have changed all the hyperparameters. This allows us to directly quantify the impact of each changed hyperparameter on the performance that we observe in the end, and in particular on the performance improvement that we observe, but it does not consider hyperparameter interactions, and it only evaluates the local importance. So what we're looking at is essentially specific to a particular pair of configurations, the initial configuration and the target configuration that we're considering here, and this might also not be reflective of what the hyperparameter optimization actually did. So even though this is obviously inspired by local search, what the local search did to get from the initial to the target configuration might be very different to what it looks like after the fact when we apply this ablation analysis. Let's have a look at an example to illustrate some of these a little bit more. I have taken the XGBoost learner again on OpenML dataset 11 balance scale, which has a default hyperparameter accuracy of about 67%, and I have improved this with an optimized hyperparameter configuration to about 76%. So now we're changing one hyperparameter at a time. So here the first change that we're making is to change rag alpha from 0 to 2.5595, and that increases the accuracy from 66.56% to 73.2799999%, so roughly 73.28%. So quite a big improvement there. Another change that we can make here to improve performance is to change the learning rate from the default of 0.1 to 1.3. This gets a little bit of a performance improvement. Then we can also change the number of estimators from 100 to 1000. This looks like it makes no difference, but then when later on we change rag lambda from 1 to 1000, we again get a little bit of a performance boost. And what you're seeing here with the learning rate and the n estimators is what I've already mentioned, that we do not explicitly take the interactions of hyperparameters into account, and this is what's happening here. There's an interaction between these hyperparameters that makes it look like changing the number of estimators has no effect at all, but the later improvement in accuracy that we're seeing when we change rag lambda does rely on this earlier change. So we cannot simply remove this change to n estimators and get the final accuracy that is shown here because of the interactions with the hyperparameters. This is unfortunately something that the ablation analysis cannot capture, and we will later on have a look at more sophisticated methods for looking at these kinds of effects as well. In summary, local search improves configurations by iteratively looking for improvements close to, in the neighborhood of the current best. It is an adaptive search as opposed to grid search and random search that we covered before. And ablation analysis can quantify the hyperparameter importance with respect to a particular pair of configurations, for example, a default and one that was optimized by hyperparameter optimization, but it does not consider interactions directly, which can lead to some misleading results in practice.